Welcome to chemistry classes. In this video we are going to discuss about part 4, chemical kinetics part 4. Clear? So in this video we are going to discuss rest of the parts of the chapter. Rest of the chemical kinetics we will discuss in this video. Clear? So today we have to discuss here first one, collision theory. First we have to discuss here collision theory. Okay. Look here, consider a chemical reaction. Consider a chemical reaction. A reacted with B produce P product. Consider any chemical reaction just like A and B. Here A and B, these are reactant, P is product. According to collision theory, reactants molecules consider like a hard sphere. Reactant molecules like a hard sphere, and these reactants molecules should collide each other effectively. After effective collision, reactants molecules change to product. So here collision theory is saying reactants molecules are hard sphere, and this hard sphere collide each other. They will collide each other during chemical reaction. Okay, there are many collision between reactants molecule. All collision do not produce product. Only effective collision gives product. Okay, these are the things discussing here in collision theory. So according to collision theory, reactants molecules assumed they are hard sphere. They are hard sphere. Okay, during chemical reaction, reactants molecules collide each other. Reactants molecules collide each other. There are many collision between reactants molecule. Only effective collision gives product. Only effective collision gives product. For effective collision, reactants should have a minimum energy. For effective collision, reactants should have a minimum energy. This minimum energy called threshold energy. Threshold energy. Okay. After that, collision frequency. Next one we have to discuss here, collision frequency. Collision frequency means number of collision that takes place per second per unit volume of reaction mixture. Number of collision that takes place in 1 second in 1 unit volume of reaction mixture. That is called collision frequency. So here we discussed, according to collision theory, reactants molecules assumed they are hard sphere. During chemical reaction, these reactants molecules collide each other. Okay, only effective collision gives product. For effective collision, reactants should have a minimum energy. This minimum energy called threshold energy. After that we discussed here collision frequency. Collision frequency means number of collision that takes place per second per unit volume of reaction mixture. This is called collision frequency. Okay. Next one we have to discuss here, two important barriers to chemical reaction. There are two important barriers. Reactants molecules should overcome these two barriers to get product. So we can check here which are the two important barriers to get product. Okay. So there are two important barriers. First one, energy barrier. Second one, orientation barrier. Energy barrier and orientation barrier. We know during chemical reaction, bond breaking and bond formation takes place. In reactant side, bond breaking takes place. Reactants molecules, bond breaking takes place. Okay, so here energy barrier we discussing here, molecule should possess sufficient energy to break the bonds of reactants. In chemical reaction, there is bond formation and bond breaking. In reactant side, bond breaking takes place. So according to energy barrier, reactants molecule should possess sufficient energy to break bond. That is one energy barrier. Second point here, threshold energy. We discussed before, reactants molecules should possess a minimum energy to get effective collision. This minimum energy called threshold energy. So these are the two important two important barriers to a reaction: energy barrier and orientation barrier. We discussed here energy barrier. According to energy barrier, reactants molecules should possess sufficient energy to break bond. Okay, that is first point. Second point, threshold energy. Threshold energy means reactants molecules should possess minimum energy for effective collision. This minimum energy called threshold energy. Okay, this is energy barrier. Next one we have to discuss here. Orientation barrier. After energy barrier, next one, orientation barrier. Okay, consider two nitrogen dioxide collide each other. After collision, N2O4, a molecule N2O4 formed. So here nitrogen dioxide, these are reactants and this is product. Okay, so according to orientation barrier, this reactants molecules should be proper orientation. This figure showing proper orientation. After proper orientation, these two reactants molecules collide effectively. Here this is proper collision. Proper orientation. After proper orientation, the first one, proper orientation. After proper orientation, there will be effective collision. Effective collision. So here two molecules are arranged. Proper orientation. There is proper orientation. After proper orientation, there is effective collision. This effective collision giving product. Okay, if there is proper orientation, there will be effective collision giving product. Second one, look here, these molecules are improper orientation. These molecules are improper orientation, not proper orientation, improper orientation. Because of improper orientation, this is nitrogen, okay, these are oxygen. This nitrogen and nitrogen not colliding directly. Here nitrogen and nitrogen colliding directly, that's why it is proper orientation. Here nitrogen and nitrogen not collide directly. Okay, so here it is improper orientation and there is no effective collision. There is no effective collision. Because of there is no effective collision, no product. Here no product, still there is nitrogen dioxide and nitrogen dioxide. Okay, there is no product. So there must be, according to this barrier, there must be proper orientation. After proper orientation, there will be effective collision. This effective collision only giving product. Okay, improper orientation produce no effective collision and not giving any product. Okay, these are the energy barrier, two important barriers of a chemical reaction. Look here, this is example for proper collision and improper collision. Here CH3Br plus OH minus. Here this one showing proper orientation and proper collision. Here there is CH3OH. Here OH attack in backside of these molecules. Okay, and it giving product. This is aqueous OH minus. Okay, here alkyl halide react with the aqueous NaOH or aqueous KOH. We will get product. And this one showing improper collision. This is improper collision. Okay, and here no product formed. So this is proper collision, this type of orientation. This is the proper orientation and here product formed. Okay, next one we have to discuss here temperature dependence of a chemical reaction. How temperature depend of a chemical reaction. Okay, look here, these are the things we have to discuss here. Temperature dependence of a chemical reaction we can explain with help of Arrhenius equation. Arrhenius equation. This is Arrhenius equation, K equal to A e raised to minus EA by RT. K equal to A e raised to minus EA divided by RT. This is Arrhenius equation. This equation helps to explain how temperature depend on rate of chemical reaction. Here K is rate constant. K is rate constant. A is Arrhenius constant. Here A represent Arrhenius constant, or it is called or you can say frequency factor. This is Arrhenius constant, or you can say frequency factor. Okay, and here this EA represent activation energy. EA represent activation energy. Activation energy mean we discussed before, reactant should pass one energy barrier to change product. This energy barrier is called activation energy. Okay, so here EA represent activation energy, R is or universal gas constant, T temperature. Clear? So here K rate constant, and here Arrhenius constant, activation energy, universal gas constant, temperature. These are the various factors. Arrhenius equation help us to understand the relation between temperature and rate of reaction. Look here, most of the chemical reaction accelerator, most of the chemical reaction depends on the temperature. When we increase temperature, most of the chemical reaction rate will be accelerate, rate will be increases. Generally, you can say generally rate of reaction or rate constant. Okay, rate of reaction or rate constant, it become twice. Okay, rate of reaction or rate constant become double when we increase temperature by 10 degrees Celsius. When we increase temperature of a chemical reaction by 10 degrees Celsius, then rate of reaction twice increases, or you can say rate constant twice increases. So this is this point saying most of the in generally rate of reaction or rate constant double by increasing 10 degrees Celsius. Okay, and here based on this we can say here temperature coefficient. Temperature coefficient mean rate constant of a chemical reaction. At this one, rate constant of a chemical reaction at a particular temperature. Imagine rate constant of a chemical reaction at temperature T. Okay, this is rate constant of same chemical reaction after increasing 10 degrees Celsius. So here temperature coefficient mean one chemical reaction conducted twice. Here same chemical reaction at temperature T, and here same chemical reaction conducted temperature T, but here we increase temperature 10 degrees Celsius. Okay, so these are the different rate constant. We will take their ratio. This ratio mentioned temperature coefficient. Okay, so these are the things, these are the different points we discussed here. Temperature dependence of the rate of chemical reaction. We discussed here temperature dependence of rate of reaction. Temperature dependence of rate of reaction. Okay, after this we have to discuss here Maxwell distribution of energy. Maxwell's distribution of energy. Okay, Maxwell distribution of energy, these are the graphical representation, and here it represents fraction of molecules and kinetic energy. Fraction of molecules with kinetic energy, how it change with the temperature. when you change temperature, what happened to the fraction of molecules with kinetic energy? Okay, look here. This is the graphical representation, and here in y-axis fraction of molecules, and in x-axis there is kinetic energy. Okay, and we showing here two graph. This is the graph, this is the experiment temperature T1, and here same graph, this is same graph T1. Okay, and we did here one more experiment, reaction at temperature T2. Okay, so here first one here at temperature T1, this is the fraction. Look here in y-axis it is fraction of molecules. So this one showing fraction of molecules with effective kinetic energy. These are the molecules, they have effective energy and they can undergo effective collision and they can change to product. Okay, so here this part showing number of molecules capable for effective collision. This is the number of molecule, or you can say fraction of molecules they can undergo effective collision at temperature T1. Okay, so when you increase temperature T2, when you increase temperature, higher temperature, when you increase temperature, what happen? We discussed before, fraction of molecules, or we can say rate of reaction or rate constant become double when you increase temperature by 10 degrees Celsius. So when you increase temperature, rate of reaction increases. Rate of reaction increases mean what? Fraction of molecules with kinetic energy or fraction of molecules with the sufficient energy will be higher, and more molecules undergo effective collision and more molecules will change to product, more reactants molecules will change to product. So look here, second graph, here T1 and T2 are temperature. You have to understand temperature T2 is higher than T1. Temperature T2 is higher than T1. So look here, this is most probable kinetic energy. Most probable kinetic energy mean here this is the fraction of molecules, higher fraction of molecules showing this kinetic energy. Okay, higher fraction of molecules showing this kinetic energy, and it is called the most probable kinetic energy. In temperature T1, most probable kinetic energy, this one. When you increase temperature, this graph will shift to right hand side. You remember always, when you increase temperature, Maxwell distribution curve, we will say these are curve. Okay, so Maxwell distribution curve will shift to right hand side. This curve shifted to right hand side. Now the most probable kinetic energy here, before it was here. Okay, so here fraction of molecules with a higher kinetic energy will be increases after increasing temperature. Okay, before or you had to say at temperature T1 only these molecules have effective kinetic energy, only these molecules have threshold energy. When you increase temperature, now look here, when you increase temperature, fraction of molecules with threshold energy increases. Now more molecules can change to product. Clear? Before at temperature T1 only these molecules have threshold energy. When you increase temperature T2, now see here more molecules, this and this, more molecules have threshold energy. Okay, fraction of molecules with kinetic energy increases at temperature T2. Also you remember at high temperature, when we increase temperature, the curve will be shifted to right hand side. When you increase temperature, the area of the curve in right hand side will be increases, area of the curve. Okay, you can say Imagine this is the graph, and here this is the area of the curve. Okay, when you increase temperature, the curve will shift to right hand side. It will shift to right hand side, and area in right hand side will be increases at higher temperature. Similarly, when you decrease temperature, the curve will shift to left hand side. It will be like this. Before it was like this, it shifted to right hand side. Okay, now when you decrease temperature, the curve will shift to left hand side. It will shift to left hand side. Area under left hand side will be increases at lower temperature. Okay, so at higher temperature, the curve will shift to right hand side, and area right hand side will be increases at higher temperature. At lower temperature, the curve will shift to left hand side, and area in left hand side will be increases at lower temperature. These are the things we discussed here. Okay, next one, look here. We know Arrhenius equation K equal to AE raised to minus EA by RT. We know Arrhenius equation. After integration, ln K is equal to ln A minus EA by RT. Okay, here convert ln to log. So we have to multiply with the 2.303. 2.303 log K equal to 2.303 log A minus EA by RT. Okay. Here 2.303. So you just imagine all this divided by 2.303. So here 2.303, here 2.303, here also 2.303. So this will be cancel each other, only this will be left. That's I did here, log K equal to log A minus EA by 2.303 RT. Okay. Look here, when you plot a graph log K against 1 by T, log K against 1 by T, here the graph will be like this, shape of graph. Okay, here slope will be EA by 2.303 R. Okay, so you remember the shape of the graph, log K against 1 by T. Okay, slope EA by 2.303. Look here, we have the equation, this equation log K is equal to log A minus EA by 2.303. Okay, so we conduct same experiment at two different temperature. We did one experiment at two different temperature. Okay, so this value will be changed like this. At temperature T1, log K1 equal to log A minus EA by 2.303 RT1. Only these things will change. K1 and T1 will be changed. Okay, T1 K1. Okay, and here temperature T2. At temperature T2 equation will be like this, log K2 equal to log A minus EA by 2.303 RT2. Okay, so rest of the things are constant. Activation energy, Arrhenius constant, okay, universal gas constant. Rest of the things are constant. So at temperature T1, K1 will be changed. At temperature T2, K2 will be changed. Okay, so two different equation at temperature T1 and temperature T2. Now you imagine this is equation number 1 and this is equation number 2. Now we have to do here equation number 2 minus equation number 1. Equation number 2 minus equation number 1. So log K2 minus log K1. Log K2 minus log K1 equal to here log A. This after deduction log A will be cancelled. Okay. Then what will be there? EA by 2.303 R, it is common, so we taken this outside. 1 by T1 minus 1 by T2. Actually we did here equation number 2 minus equation number 1. So we have to get 1 by T2 minus 1 by T1. 1 by T2 minus 1 by T1 we have to get, but there is negative sign. Because of this negative sign, we did like this 1 by T1 minus 1 by T2. Clear? Now see here 1 by T1 minus 1 by T2 after solving, okay, we will get T2 minus T1 divided by T1 T2. And here log K2 minus log K1 we can write like this log K2 divided by log K1. So remember this equation, log K2 divided by log K1 equal to EA divided by 2.303 R times T2 minus T1 divided by T1 T2. Okay. So this is the things we discussed now. Okay, next one we have to solve some sample problems related to this chapter. Okay, look here, a first order reaction, first question, we are talking first question, a first order reaction has a rate constant is given 1.15 into 10 raised to minus 3 second inverse. How long it will take to convert, how long it will take to change 5 gram sample, 5 gram substance to 3 gram. Okay, so here the question saying it is first order reaction, rate constant is given. Okay, how long it will take? So you have to find T. Okay, initial concentration, initial amount of substance 5 gram change to 3 gram. So to change 5 gram to 3 gram, how long it will take? This is the question. We discussed in second part of this lesson, second part of this video, we discuss first order reaction. This is the equation for first order reaction. Okay, K equal to 2.303 divided by T log A0 divided by A. This is the equation. Here rearranging this equation, T equal to 2.303 divided by K log A0 divided by A. Here K rate constant, T time. This is we have to find log A0 divided by A. A0 mean initial concentration, A mean final concentration. So all the data are given here. You just substitute 2.303, 1.15 into 10 raised to minus 3 log initial concentration. This is the initial concentration and this is the final concentration. So log 5 by 3 concentration, or you can say initial amount. Okay, initially its amount 5, at the end of the reaction 3. So here log 5 by 3. Log 5 by 3 means 0.22 into 118. Okay, 0.22 into 18. Okay, so after solving this you will get 444 second. Look here, rate constant given in second. So the answer will be in second. I told you in the previous video, if here minute, we have to put here minute. Clear? Okay, next one, question number 2. Question number, sample question number 2. Here question saying the rate constant of the first order reaction. Again here it is first order reaction. Rate constant is given 60 second inverse. Rate constant 60 second inverse. How much time it will take to reduce the initial concentration of reactant to 1 by 16th. Okay, so here in this question it is first order reaction, rate constant is given 60 second inverse. You have to find time to change initial concentration of a reactant to reduce 1 by 16th of initial value. You have to find the time. Okay, so here initial amount and final amount not given. So we have to assume initial amount of this reactant A. Okay, and final amount is 1 by 16th A. Initially it is A. Finally it's 1 by 16th part only. Rest of the part consumed. Okay, so now we have initial amount and final amount. Okay, this type of question you have to do like this. Here no initial amount, final amount, so assume initially a and finally 1 by 16th a. There are many questions related like this, so you have to follow this method. So here you have to find the time. Okay, also I told you it is first order reaction. 2.303 divided by K log initial concentration minus final concentration. We know initial concentration A, final concentration 1 by 16th A. So this term will be cancel each other. Okay, if you take here initial amount X 1 by 16th X, then this term will be cancel each other. So 1 by 16th will be left over there. Okay, 1 over 1 by 16th. Okay, so it will be log 16. This 16 will come up and it will be log 16. Log 16 mean 1.204. 1.204. After solving this, you will get this answer. Again, look here, rate constant in second inverse. So here time, it will be in second. Number 3, question number 3. Here we have to do one thing. Here question saying rate of a particular chemical reaction triples. Rate constant, not rate constant K, rate constant of a particular chemical reaction triples, became 3 times when temperature increase from 50 degrees Celsius to 100 degrees Celsius. Calculate activation energy for this chemical reaction. One chemical reaction, okay, its temperature was 50, initial temperature T1 50, okay, 50 degrees Celsius. Then we increased temperature to 100 degrees Celsius. Okay, so at temperature T1, rate constant K1. At temperature T2, rate constant K2. Imagine K1 is equal to K. At temperature T2, at 100 degrees Celsius, when you increase temperature, rate constant became 3 times. K became 3K. K became 3K. Okay, so K2 divided by K1 will be 3K divided by K. K will be cancelled. So K2 divided by K, it will be 3. Okay, so we have to use here log K2 by K1. That's why I found here K2 by K1. Clear? So this is the question. I will repeat the question. Rate of a particular chemical reaction. Rate constant of a particular chemical reaction triples when temperature change from 50 degrees Celsius to 100 degrees Celsius. Then you have to calculate activation energy. What will be activation energy? So it is saying it is first order chemical reaction, or you know, this is this equation we derived from temperature dependence of a chemical reaction. Log K2 divided by K1 equal to EA divided by 2.303 or T2 minus T1 divided by T1 T2. This is the equation. Okay, here R also. Okay, so all data is given in the question. Okay, here I found log K3, log K2 by K1, it is 3. So log 3 equal to EA divided by 2.303. R is given in the question, it is 8.314. Okay, and 50, 100 I will change to Kelvin by adding 273. Okay, so it will be like this: 373 minus 323 divided by T1 T2. 373 times 323. Okay, now see here, 373 minus 323, it will be 50. So EA times 50. Rest of them I did all here: 2.303, 8.314. Okay, all together. So after solving this, log 3 mean this is log 3. This is log 3. Okay, so to find EA, you have to find EA. Bring all these datas over here. Okay, so it will be 0.4771 times 2.303 times 8.314 times these things. Okay, it will be here on the top divided by 50. All this will be up divided by 50. That will be EA. After solving this, you will get 22012 joule per mole. Joule per mole. Okay. To convert this into kilojoule per mole divided by 1000. So you will get 22.012 kilojoule per mole. This is the answer. Activation energy. Okay. Next question. According to next question, here it is given the decomposition of hydrogen peroxide. Decomposition of hydrogen peroxide follows this equation. Okay, decomposition of hydrogen peroxide follows this equation. K equal to 4.5 times 10 power 11 second inverse times e power minus 28,000 divided by t. It follows this equation. Okay, here the question asking find activation energy of this chemical reaction. Find activation energy of this chemical reaction. I will read the questions again. The decomposition of hydrogen peroxide follow this equation. Okay, and here calculate activation energy. We have to find EA. We know this equation is much similar to our Arrhenius equation. This equation is much related to Arrhenius equation. Okay, K equal to e power minus EA by RT. Okay, K equal to one constant, e power minus 28,000 divided by T. But there is R, here no R, only this different. Okay, comparing these two equation, we can say minus EA by R. Okay, here T is here, also here T is here, so we can cancel that term. Okay, rest of the part we will write here. Okay, look here, K is here, okay, and here K equal to A e raised to, according to Arrhenius constant, K equal to A e raised to minus EA by RT. Instead of A, this is constant, we have a constant value is given. So we can say minus EA by R equal to minus 28,000. So you just connect this equation with the Arrhenius equation. That is the logic of solving this question. After that, normal steps. Minus EA by R equal to 28,000. We know R is equal to 8.314. So after solving this, you will get EA is equal to this value. Okay, to convert this divided by 1000, so 232.792 kilojoule. Thank you for watching this channel. Please subscribe and press the bell icon for more videos. Thank you.